Today's step question is a probability question. A question 11. These questions aren't attempted by many candidates, and when they are attempted, they aren't always done successfully. Is that because people are put off probability and don't like it? Maybe it's because the questions are wordy, or maybe because, being the last question in the paper, candidates don't have enough energy to tackle them. Anyway, a lot of these questions are very tackleable with a little bit of practice. And so today's I'm going to go through. It's from 2019. It is question 11. And you can see plenty of words in this question. So it's two people adopt the following procedure for deciding where to go for a cup of tea. Either a hotel or a tea shop. Each person has a coin with probability P of heads and Q of tails. There are different rounds of this procedure. They both toss their coins once. If both show heads, they go to the hotel. If they show tails, then they both go to the tea shop. Otherwise, they continue for the next round. And this is repeated until the decision is made. You may recognise this as a geometric distribution question, but even if you don't, there's not much probability in this question. Show that the probability that they make a decision on the nth round is q squared plus p squared times 2qp to the n minus 1. So analysing the situation. So for the first round, they can go to the hotel, and the probability of that is p squared. Or the tea shop, and the probability is q squared. And moving to the next round, that probability will be 1 take p squared take q squared. This is just using the and the not laws. Now here's some algebra. P plus q squared equals p squared, add 2pq, add q squared, binomial formula. So 1 take p squared take q squared equals 2pq. The chance of a decision on the first round is q squared add p squared, and the chance of no decision is 2pq. So what's the chance of a decision on the second round? Well, on the second round, that implies a decision has not been made on the first round. So we have 2pq, and then it is made on the second round. That's q squared plus p squared. So the analysis of this situation is every time we're going to have the p squared plus q squared, and we're going to have 2pq's as many times as is needed to get to that round. So in general, on the nth round, we've had n minus 1 rounds with no decision. That's 2pq to the n minus 1. And then we have a decision on the nth round, which is q squared add p squared. Back to the question. Now we've got that, show also the probability they make a decision on or before the nth round is at least 1 take 2 over n, whatever the value of p. So this isn't really about probability, this is about adding up series. So a decision on or before the nth round, we have n terms of the geometric series. Q squared add p squared times 2qp to the 0, add 2qp to the 1, through to 2qp to the n minus 1. Using the formula for the sum of a geometric series, we get 2qp to the n minus 1 over 2qp minus 1. And then, since q squared plus p squared equals q plus p squared take 2pq, that's 1 take 2pq, the whole sum of the series simplifies to 1 take 2 qp to the n. Now the question says to show that this is always greater than 1 take a half to the n, so we need to maximize 2pq subject to the constraints that p and q are positive numbers between 0 and 1, and p plus q is 1. Now the answer to this is fairly easy to spot. It's when p equals q equals a half, in which case 2pq also equals a half. But we need to justify that. We can't just state it. And you could do this by differentiation, completing the square, or other methods. I'm going to use the famous arithmetic mean, geometric mean inequality that says that for any two positive numbers, the geometric mean, the square root of pq, is less than or equal to the arithmetic mean, p plus q over 2. And we have equality only when p equals q. So squaring and multiplying by 2, 2pq will be less than or equal to p plus q squared over 2. And in this case, p plus q equals 1, so that's a half. So we have the maximum value of a half when p equals q equals a half. So the minimum value of the probability is 1 take a half to the n. Part 2 of the question. This time we're going to have 3 people doing something similar, not quite the same. We need to read it carefully. 3 people adopt the following procedure. They each have a coin, probabilities p and q again. They all toss the coin. If all 3 show heads, they go to the hotel. If they all show tails, they go to the tea shop. Otherwise, we continue to the next round. Now, if they continue to the next round, either we've got 2 heads and a tail, or 2 tails and a head. So what happens in this case is, the 2 who have the same face toss again, but the third person just turns over his or her coin. If now all 3 coins show heads, they go to the hotel. If they show tails, they go to the tea shop. Otherwise, they move to the third round. And the question is to show the probability they make a decision on or before the second round is at least 7/16. So this is the only part of the question where we really need to apply some logical thought to the probabilities here. For the first round, the probability of a decision on the first round will be p cubed add q cubed. That is 3 heads or 3 tails. If they don't get that, they go to a second round. And they either got 2 heads and a tail, or 2 tails and a head in the first round. So case 1, if they got in the first round 2 heads and a tail, the tail turns over to make a head, and the 2 heads toss again. And they need to get heads, so there are 3 heads, and then they will go off to the hotel, and the probability of that is p squared. If in the first round they had 2 tails and a head, the head turns over the coin, the 2 tails need to toss again, and they need to get tails again for them to move off to the tea shop, and the probability of that is q squared. So, being careful about the outcomes here, so if in the first round they got 2 heads and a tail, the probability of that was 3p squared q, the 3 because of the 3 orderings, and then we need 2 heads in the second round, and the other possibility was 2 tails and a head in the first round, the chance of that being 3p q squared, and then 2 tails in the second round. That's q squared. So overall, the probability of a decision on or before the second round, in the first round it was p cubed add q cubed, and in the second round it's 3p to the 4q add 3p q to the 4. All we have to do now is to find the minimum value of that as p varies, and we're done. So, there's a number of ways of tackling this. It seems to me a sensible way would be to take 3pq out of brackets and then factorize to get p cubed add q cubed times 1 plus 3pq. p cubed plus q cubed can be tackled using the expansion of p plus q cubed. Subtract 3p squared q minus 3pq squared, which is 1 minus 3pq times p plus q, so 1 minus 3pq. So the overall probability is 1 take 3pq times 1 plus 3pq. A difference of 2 squares, I think that's nice. 1 minus 9pq squared. So we need the maximum value of pq in this question. We did that in part 1. We've already justified the maximum value is when p equals q equals a half. Then pq is 4 a quarter. So the probability will be for all p and q values greater than or equal to 1 minus 9 times a quarter squared, 1 minus 9/16, and that is 7/16. So quite a nice question. The key issue for probability was the cases in part 2, but you're not really asked to do anything in this question apart from use the basic laws of probability and some logical thought. I claim these questions are very tackleable with a little bit of practice. We did need to justify the maximum value of pq and use the favourite formula, p cubed add q cubed equals p plus q cubed take 3pq p plus q, which is used in step questions, not only here in probability, but also in questions about the roots of equations. So that was the last question in the paper. I think these questions are well worth tackling and practicing. They are easy marks with a bit of practice. So that's the end of this paper. Next time we'll do one from a Step 2 paper. For now, this is Gold Standard Maths, and I'm David Forster.